Welcome to Grumpy Science, and we're going to talk about old science.
We're going to get really grumpy on this one.
Grumpy, really old, not grumpy old scientists like us, but we're talking about science from a long time ago, because some of it's really good.
And interestingly enough, we actually stumbled across a paper. We were reading one guy. We won't mention his name, but boy, he was even grumpier than we are.
Oh, yeah.
He got really upset.
Yep, absolutely.
So one thing we were talking about was like the way they started doing sensory perception tests back in the 1860s. As you know, with our product placement, the brain gauge.
Civil War era, right?
Yeah,
so this
the
is
brain
like
gauge actually does sensory perceptual tests, which is probably the most sensitive way to detect changes in brain health. That's something that people still hadn't really grasped hold of, because they say, now let's go get an MRI. Hey, I hit my head, and they go and get an MRI, they get a scan. And Bob, you know what it shows?
Yes, I do know what it shows. I'll sum it up in a word, and correct me if I'm wrong. Nothing.
Correct. Nothing. So people spend tons of money on this kind of stuff.
Images are really, really good for medicine because they're really easy to bill.
Yeah.
At multiple levels, like taking the image, interpreting the image, telling you that you don't see anything. All of that's really expensive.
Yeah, if there's bleeding or something in a certain spot.
Yeah, that's true.
Yeah,
I mean, you've got a massive
lesion.
lesion. Like, what's that fence pole doing in the guy's head?
Yeah.
You'll see that for sure.
Right.
But, the kinds of injuries you get from a mild to moderate TBI, I think is, correct me if I'm wrong, you're the expert, but I don't think they ever show up in an image. I mean, really.
Not really. Though some very
Exceptions.
expensive imaging techniques can detect some subtle changes, but it's really not
well, it's not
effective enough
commonly
to be a
available.
diagnostic.
It's not effective enough to be a diagnostic. It's not commonly available. So
So basically what we're talking about are changes that are, if you take group A and group B and you do all these measures, and you can show an 8% difference.
Oh, that's right. So a lot of these things on images that can actually show a difference, you have to be looking at groups of people, not individuals. Is that correct?
Right.
That's actually kind of a big deal.
Not really a
so like if your
diagnostic.
kid gets hit in the head playing soccer, you'd have to bring like 12 of that kid that got hit in the head and 12 of that same
Under
kid
the
that
same
didn't.
condition.
Under the same condition.
Under the same
And
age,
then
same gender,
it would
same
take a bunch of
genetics.
images of all these identical children under identical conditions.
Yeah.
It doesn't work that way, right? I mean,
Yeah.
you got one kid that
Yeah.
got hit in the head. So even theoretically, those imaging modalities. that
We
could
had
work, they don't.
we had an interesting concussion study where two guys were lined up against each other. They both hit their heads together.
Oh, God.
But you know what? They didn't have the same data. They apparently had bothered one more than the other. Some people's heads are harder. So, back back on track, since we have a tendency to get off track.
No, we don't.
No.
We're laser focused here on Grumpy Science.
Yeah, actually,
we go
I like to
straight
think
for
about
the
when
grumpiness.
Well, I like
all else is secondary.
When you're talking about that temporary blindness you get from focusing, without
Retinal fade.
Retinal
you
fade.
Can look it up. Yeah, it's
Well,
real.
I never experienced that because I don't have an attention span that long.
Yeah.
That would require me.
There is actually a kind of a gross way to do that, right? Where you can press on the side of your eye and hold your eye still. And I was required to do this in graduate school, and stop your eye from saccades, and all of a sudden it's still, and you hold your head still, and in about 4 seconds the entire field goes gray, and your first response is, oh my God, you went blind. You let go of your eye, and your vision comes back, right?
Okay. Do we need a disclaimer on that? So don't try this at home.
For the love of God, kids and grandparents and everybody else, don't poke your eye, all right? I'm telling you, it's gross. It's very uncomfortable, but it's real. And it's one of those things. It's an interesting thing. It's like people don't realize that if you don't keep moving your eyes, you actually go blind.
Yeah. So anyway, we were reading this grumpy paper, and the grumpy author, the paper wasn't that grumpy, but the author was. But anyway,
which we like a lot. These are people we shout out to.
So because we look at, whenever we do a study, we look at it historical context, and it's really important to basically look at the people who did stuff, a long time ago. And there is a trend amongst what do you say, youngsters?
Youngsters, anybody that's like a month younger than me. Young kids.
They sort of don't think anything before about 2010 is valid.
Actually,
in the literature.
There is kind of an alarming tendency of people to think that the world of knowledge started 10 or 15 years ago. But there's a huge body of science that's really good because it was done really carefully, because it was really hard to do. Instruments were harder to make 100 years ago. So
Exactly.
you'd make an instrument, and it's really a precious thing. Number two, a lot of old-timey scientists were actually excellent instrument makers, so they understood what they were measuring because they built the thing that was doing the measurement.
Exactly.
You very rarely see that anymore. A great example, did I ever tell you about my conversation with Andrew Huxley?
Oh, no.
Okay, so Sir Andrew Huxley, all right, from the Huxley-Hodgkin equation, Nobel laureate. He passed away a few years ago, but he and I were having beers, believe it or not, in Ann Arbor, Michigan. We were talking about stuff, and he was telling me, now he's the guy who invented hydraulic micromanipulators to, like, which you see all the time for, like, IVF and different manipulating cells and pulling stuff in and out. He invented a lot of stuff, and he made a lot of his own instruments, and he basically formulated a lot of what we understand about how nerves work by working on the giant axons, right? Mm-hmm. And he built his own instruments to measure these things. And so he and I were talking about neurophysiology, the history of it, but what we're talking about is scientific instrument builders, and it's very interesting when you really understand what you did and why you did it, what you measured, and how reliable how good that measurement was. And that's something that's almost entirely missing from modern science, and this is what Mark and I are getting at. So sometimes we go back to these old scientific experiments. Who was it that I talked about? Galvani. I think Luigi Galvani, 1791 or something. Really good stuff.
But so we were looking at writing up our reaction time data. And so let's go back to the original papers and the original people that we studied reaction time, and they were looking at it, and they were very, and if you read any of these old papers and compare them to modern papers that are much more, all they want to talk about is this molecule did this or this, whatever.
Molecules do things.
They
do, but that's not where the story ends.
Okay?
Yeah, there are emergent properties in systems.
But, they get very philosophical in the old papers about what you're thinking about and what you're measuring. And reaction time was actually one of the first sensory perceptual measures that people said, and they found a lot of different changes with that, but they measured it very precisely with a chronograph.
Which is basically a moving piece of paper and a pen.
Yeah.
Okay, so a motor.
So they knew the velocity of the paper.
Yeah, exactly. So then they got this pen, like every time, they'd zap somebody or something. It was one of the stimuli they used.
Electrical stimuli to the toes.
You have to have very enthusiastic subjects to do that, I think, is one of these things.
But they are extremely accurate. I mean, these guys are really accurate.
Tremendously accurate. And this is before the transistor, right? I mean, this is...
So basically from the 1860s until the 1950s, you can read all these papers, lots of papers about reaction time being used to measure the effects of different neurological insults, and you can actually learn a lot just from reaction time. Mm-hmm. And even in the 1950s, there was a guy that wrote a paper and very thoughtfully he said, tactile reaction time is actually the best, except nobody really wants to do it because there are no stimulators that are proper that can deliver it.
Hard to do, right?
Really hard to do. And there's reasons that biologically tactile stimulation paradigms are better than visual stimulation, especially for reaction time. And, it's basically got to do with fidelity of the signal. But that's not really the point of this story. It's just another sidebar.
We can go on
and on. But
sometimes we do.
But let's go on and say, people all of a sudden, people decided, hey, we got this here computer. We can flash something up on it
when you're a hammer,
and
you think the whole world's
and then have somebody click on a mouse, and that'll give you a reaction time.
So
and they'll say it's very precise because we can get precision down to 0.32567 milliseconds. But guess what? I think we discussed the difference between accuracy and precision before, but it probably wouldn't hurt to remind people what the difference is.
Accuracy means that the number that you're giving actually represents reality. Precision means the number that you're giving has a lot of digits in it, like 2.7454264, but it's not on target. It's way different from reality.
I can tell you my age is 35.363241.
Exactly, which is precise,
very precise,
but inaccurate.
It is kind of inaccurate.
When you do, like, especially online reaction time testing, that involves, scripts being downloaded for every thing.
They actually, and people
can be off by,
basically, so here's where you have basic latencies and delays. You got computer hardware,
a mouse.
You've got the flashing screen to give the stimulus. Okay, and screens flash at a certain frequency.
Refresh rate.
A certain refresh rate, so there's an error right there. You got the operating system that also introduces error. And then you've got, on the response side, you also have more software problems. And, people say, yeah, but you can just subtract out of those problems and all this.
They're not constant. That's the thing. Operating systems are juggling dozens or hundreds of things. And they're saying, okay, reaction time test, you're going to have to wait 10 or 15 milliseconds, which is kind of the whole story. And you're just waiting there while the computer's doing something else. So you're not getting good data. And this is what's really interesting. Mark and I reviewed a very bitter, grumpy series of papers recently to write a paper of our own on. That's hopefully at least as grumpy. Can we say the guy's name? Yeah, he's published.
He's published, but
right?
Yeah.
Plant.
Anyway.
So shout out to Dr. Plant, okay, at York, because he's right. And he's been pointing out for a long time, almost a couple decades, that, the more people use higher and higher speed computers, the less accurate their reaction time test data is, because more and more stuff is being done by the computers, and mice and things become cheaper, and he calls them commodity grade.
But there's even differences between computer systems. So
computers at different times under different loads behave differently.
Right, and so all these things are dependent on and a lot of these computer programs that do cognitive online assessments. In other words, when you send your kid to high school or college, and if they're participating in sports, they're going to take we won't mention that name, but there's a very common test that they take. Oh, we're going to do baseline. Well, the baseline responses on these things are horrible, because there's anywhere from 100 to 300 millisecond delay, and that number,
it's variable.
Well, that number probably doesn't mean anything to you, but let's just
a tenth to a third of a second, which is large compared to the actual reaction time of a young athlete.
So that most of these kids, or normal healthy kids,
rubbish.
Their reaction time is going to be about 200 milliseconds, and that's an important score. Okay,
but you're adding noise because of the way that it's measured on computer. That's that size roughly.
But you can add 100 milliseconds to it,
or more or less, and it's variable every time.
But Professor Know-it-all, you're going to do this over and over and over and get an average.
The same computer, and you got exactly the same number.
Yeah, you do the average over and over and over, and you find, okay, well, this guy roughly 200 to 300 milliseconds, somewhere in there, and then if he gets concussed, he's going to be somewhere between 250 and 300 milliseconds. He might be a little higher, but it's really not very accurate. And it's like, why do you want to use crappy stuff?
Well, this is the thing. So, why do you want to use crappy stuff? Sounds like a rhetorical question, but it's not. It's actually a really serious scientific question. Why would you use something like a computer mouse and keyboard and a monitor screen to make a precise scientific measurement when it is not physically possible to do so? And yet the vast majority of things where people are now doing physiologic measurements, with different smart things that you can buy and put on your body, a lot of these are really, really variable, right. Not accurate. They're very precise. They're just not accurate.
Well, and it turns out the accuracy of the mobile device is even worse.
That's the worst.
And it's really not designed for scientific instrumentation.
No.
You know of something that might be designed for scientific instrumentation?
I do, and it's our product placement of the day.
Product placement of the day?
The brain gauge. So, when you read these old papers, and the new papers talking about the old papers, they say basically in order to make a good measurement, you have to have something that's doing one thing and one thing only, very precise timing measurement. And it doesn't have all kinds of other interfaces and network connections and overhead load like, in an operating system that you can't predict or correct or subtract for. And so what the brain gauge does is it does, timing-wise, it does one thing and one thing only. It's got dedicated internal timers that are very precise.
So just to give you some numbers, the average reaction time emission was 200 milliseconds, but a measure that's even more important, which actually we've done the scientific study on the side of this, is that reaction time is pretty important, and we show really high significance that you see differences with that with neurological insult. Yes. And the number that's even more important is reaction time variability.
So how consistent your reaction time is, right?
Right.
Or how variable it is.
So you can imagine that if you're taking a test, a reaction time test, and you feel something and you respond to it.
It may be that your reaction time is 200 milliseconds, 0.2 seconds, but the variability might be It's a lot tighter than that, right?
A lot tighter. Well, if you're healthy,
I mean,
you're going to be within anywhere from 3 to 20 milliseconds. So we see people around 3 to 5 milliseconds all the time.
But if you're adding all this random noise from all these cheap computer peripherals that's an order of magnitude 10 times more than that already, there's no way that you can mine down to an accurate measure of that signal. Right. And so people have used all kinds of things, a central limit theorem and all kinds of like sort of, you know, mathematical rationalizations for why it's okay to use crappy instruments. But it's not okay.
So we see reaction time variability, like I said, for normative values between 5 and 20 milliseconds, and when people get concussed, for example, it pops up to 40, 50, 80 milliseconds. If you are using this crappy instrumentation, you won't be able to get a reaction time variability. I mean, it's going to introduce reaction time variability.
Give you a number, boy, it
in the 50 millisecond range,
precise number, but it won't
you
be
can't measure.
At all.
It's not accurate at all for getting reaction time variability. So that's a good reason not to put a lot of trust into some of these things.
So this is the thing: if you're really interested in your somatosensory performance, reaction time testing, any of these kinds of tests, there's a very strong draw to, you know, hey, I know how to develop mobile apps. You know, I'll just develop an app. I've got everything I need in my mobile device, or I'll just do it, you know, and write it in Python and do it on my computer and everything. These devices are really good at certain things, but they are terrible, terrible devices, and there's no way to fix it inherently because of how they work. So if you're going to actually try to measure the function of your brain, you need a dedicated device, and that's what the brain gauge is.
And imagine doing a study that's funded, and then basing it off response time latencies of computer hardware like that, and then publishing a paper, and then having to have it retracted that's
a good point. It happens not often enough, but some of the braver, some of the more courageous scientists will come forward and say, you know what, we're going to retract this paper now that's been published, which is deeply embarrassing for a scientist to do. Yeah. To say, you know, but it's happened, and even recently where they'll say, well, actually our instruments weren't as accurate or reliable as we thought, and so this data is rubbish, and we have to pull this paper back. That's a terrible, terrible thing. It's like, you know, much worse than admitting to one of your friends you were wrong or that you stole. And I didn't steal anything from you. I'm just saying, you know, no
You didn't take my lunch money?
I didn't take your lunch money. But it's really hard to admit that you're wrong as a scientist because, man, that sticks with you for life, right? But even still, we get there's a whole thing about this retraction watch, you know, and they're watching to see who's pulling their papers back. And there's a whole problem with the replication crisis in medical literature, biomedical literature in general. And one area where they're acutely aware of it now, I think, because of these grumpy people.
One reason we developed the brain gauge
to combat this
was basically so that people could do, well, in the initial stages, so that people could do decent research with very accurate instruments.
Anywhere can use this instrument. Yeah, it does network and it does go over the internet and all that stuff. But all the errors that are associated with commodity grade, you know, cheap human interface devices, those are all gone, and built into the brain gauge are all the things you need to have to actually make an accurate measurement.
So, you know, we've dumped a $50,000 scientific laboratory into a
computer mouse.
Into
$50,000
in a computer mouse sized device.
I mean, seriously, it would cost more than that to buy the instruments that you would need to make the same measures that we make, you know, with a brain gauge. But the point is that it's not a computer mouse, and if you see somebody else come along with one with, like, you know, cell phone vibrators in it, and they're going to tell you about how it measures your brain, or if somebody comes along with an app that's got like a computer mouse on it to simulate, you know, or anything else, that stuff's rubbish because it's using hardware and firmware that is not capable, not even theoretically capable of making the measurements that you need in order to get accurate assessment of brain function. So this was not a very funny. We're almost as funny as grumpy cats. But this time we're not.
We went back 150 years, so it did take a few minutes.
It was kind of old timey, but we kind of want to, you know, we wanted to emphasize old science is better in a lot of ways. One of the things Plant pointed out in his most recent letter was that the science of measuring reaction time and everything is getting worse and worse over time, because people are sloppier and sloppier with cheaper and cheaper instruments, right? So anyway, we're combating that trend, doing old time science in a modern way.
Yep.
That's what we're doing. All righty.
All right.
Thanks.
Thanks for coming.